Hello, or bonjour, and welcome to the Astrophysiciens and Astrobiologists, a symposium co-organized by the Consulate General de France at Toronto and the Origins Institute in collaboration with the McMaster University Alumni Association. My name is John Stone, or I suppose Jean-Pierre. I'm privileged to be the director for the Origins Institute at McMaster University, fiercely proud that the Institute itself can populate the Canadian contingent in the program, and excited to initiate collaboration with the French consulate and stellar researchers constituting the French contingent in the program. My partner in this public endeavor is Eloi Astier, Science and Technology Project Officer, Culture and Science Service, French Consulate. Outreach is important to the more than 70 research centers and institutes at McMaster University and the 5 in the Faculty of Science. And we are fortunate to be partnering with the Alumni Association as well as interacting with you. I now introduce Dr. Maureen MacDonald, Dean, Faculty of Science, whose support is appreciated greatly. With some deans, that support effectively would be financial, but with Dean Maureen, support flows in a variety of forms, including financial, but also extending to moral and what I would call academic ergonomics. We welcome Dr. MacDonald for introductory remarks.
Thanks so much, John. Good morning, everyone. Thank you so much for joining our transatlantic event that has certainly intergalactic and interstellar focus. I want to personally thank what I understand to be the very dynamic duo who organized such an amazing series of talks over the next 2 days. Jonathan Stone, who you just met, is the director of the Origins Institute in our Faculty of Science here at McMaster University. And it's wonderful to hear that you're so very proud of all of our institutes and centers, and we are as well. And we really appreciate the leadership role that you've taken in the Origins Institute over the last year, Jonathan. And Eloi Astier, the Science and Technology Project Officer with the Consulate General of France in Toronto. It's wonderful to see when collaborations come to life in these types of very important and impactful outreach activities. I understand that Eloi reached out to Jonathan back in January. They'd originally planned to hold an event with 2 speakers, one from McMaster and one from France. But in true collaborative style, that idea quickly grew, just like the Origins Institute, into 2 days of talks with renowned astrophysicists and astrobiologists, plus graduate and undergraduate students. In organizing this event, Eloi and Jonathan have made history, or rather, herstory. All of the scientists and students presenting over the next 2 days are women. This would not have been the case 20 or even just 10 years ago. At best, there may have been one woman speaking at the event, likely on a panel and definitely not delivering the keynote. I want to congratulate Eloi and Jonathan for building an entire program with an exceptional women scientists who will in turn inspire girls to follow their lead and look into the sky. I also want to thank Eloi and Jonathan for their spirit of collaboration. Collaboration clearly defines not only our Origins Institute, but all of our research centers and institutes in the Faculty of Science. Our 5 centers are led by outstanding researchers like Jonathan. They bring together faculty members and students from across departments and disciplines, and as with today, forge partnerships with academic, industry, community, and government partners. These collaborations are actually key to creating the wealth of knowledge and the incredible diversity of perspectives and experiences that we know are at the foundation of outstanding science. In the Faculty of Science, we fundamentally believe that diversity leads to better questions, better answers, and therefore better science. And that diversity of voices and perspectives is vitally important to the Origins Institute. This institute is searching for answers to some of the most interesting and important questions in all of science. How did the universe begin? How did elements form? How did stars, galaxies, and planets form? How did life emerge on Earth? And has it also emerged on other planets? Thanks to Jonathan and Eloi for bringing together such renowned scientists and students who are sure to make their own mark as astrophysicists and astrobiologists in the future. Thank you so much. Enjoy your next 2 days and make sure that you take some time to look at the night sky. I'll turn it back over to you now, Jonathan.
Thank you very much, Maureen. I'd now like to introduce the first presenter. Dr. Laura Parker is a professor and university scholar at McMaster University. Dr. Parker came to McMaster in 2007 after a postdoctoral fellowship in Munich, Germany, and a PhD from the University of Waterloo. Dr. Parker and her research group use ground and space-based observations to explore how galaxies in the universe form and evolve over cosmic time. In the first time slot in this cosmic program, Dr. Parker will describe for us galaxy evolution in dense environments.
Thank you, Jonathan. So I'm just going to share my screen, and if you could confirm before I start that it is working, then I will get started.
Perfect.
Great. So I'm very happy to be here today to discuss some of the research we've been doing in my group on how galaxies evolve. So what I mean by that is how they change over time and how that depends on the environment in which galaxies live. So if all of those ideas sounded new to you, that's okay. We're going to discuss what are galaxies, what is galaxy environment, and what does galaxy evolution mean today. So I thought I'd start with just a few beautiful images of my favorite objects in the universe, which are galaxies. So galaxies, like these ones on the slide, are huge collections of stars and gas and dust and complicated many processes happening all at once. And trying to disentangle all of the things that happen within galaxies is a big endeavor. And so no one does all of that. We all work on our own little pieces of the puzzle. And I'm going to describe to you today one of the things we're working on in my group. So on this slide, what you can see on the left are two interacting galaxies. And these happen to be what are called spiral galaxies. We're going to see on the next slide what those are all about. On the right, upper right, we have another spiral galaxy. And on the lower right, we have this big orange blob. That's a giant elliptical galaxy, a different shape. And this is a galaxy living in a rich collection of many galaxies called a galaxy cluster, which we're going to learn more about today. So when you're looking at pictures like this, these are optical pictures. So that means they're taken at visible wavelengths, the same kind of light your eye can see. And these are all from the Hubble Space Telescope. So these are beautiful high resolution pictures from Hubble. And if your eye were 2.5 meters large and you could open it for a really long time, this is what you would see. These are the wavelengths of light that you can see. We can learn more about galaxies at other wavelengths as well, but I'm going to focus today on the visible picture. So those were a few highlights of some really beautiful galaxies, but it's useful to have some categories in mind of the basic kind of types of galaxies. So this is a modern version of a classic diagram called the Hubble tuning fork. And so this is a rough picture of the main types of galaxies. And on the left, we have these big orange fuzzy blobs like we had in the bottom right on the previous slide. These are called elliptical galaxies, labeled with E's. And on the right, we have the spiral galaxies. And the big difference between the left and the right is on the left, the galaxies are really three-dimensional. They're ellipsoidal in shape. And on the right, the spiral galaxies, you can picture looking a little bit more like a frisbee. So very big if you see them face on, and thin if you see them edge on. But it's not just the shapes of galaxies that change as we move from left to right. It's also, as you can see right away, the colors as well. And so as an astronomer, what we know when we see a galaxy that looks orange, like the ones on the left, that tells us that that galaxy has not had very much star formation recently. And you're going to hear more about star formation throughout the talks today and tomorrow. And on the right, if you see galaxies that look bluer, the blue color is telling us, oh, these galaxies have had some recent star formation. Hot, young, very bright stars are blue in optical color. And so just by looking at the color of a galaxy, we can figure out if it's had recent star formation. So we now know that on the left, the galaxies are three-dimensional, don't have much star formation. We've also, from other observations, we know they don't contain much gas. And on the right, the galaxies are much more gas-rich, still undergoing star formation. And so as an astronomer who studies these galaxies using observations, I want to understand why. Why do we have this diversity of galaxy shapes and colors and star formation rates? And how do these properties change over time? And what does that depend on? And so one other piece before we dive into some of the work we do on galaxy evolution is I wanted to remind everyone or introduce the idea that when you see a galaxy like this, a nice spiral galaxy, and this is a visible picture, optical light, when you see a view like this of a galaxy, you're not seeing everything. For one reason is because there's other physical processes that emit light at different wavelengths. So not all of the light comes out in the visible. So of course, galaxies would look different if you had an ultraviolet telescope or an X-ray telescope, and we can use those to understand galaxies. But on top of that, there's the most dominant component of a galaxy in terms of its mass is something we don't see at all. It doesn't give off any light, and that's called dark matter. So unfortunately, in the interest of time today, I'm not going to get to discuss dark matter in detail. We may hear more about it later this morning, and I'm happy to take any questions. But what I want you to keep in mind is that when you see a galaxy, the visible light that you see, it's embedded in a much larger structure that we call a dark matter halo. That's most of the mass of the galaxy. And on top of that, galaxies themselves are embedded in the large scale structure of the universe. So galaxies are not little islands. They live as part of a much larger cosmic structure. And so this is actually an image, a slice from a simulation of structure formation, but we can also see this observationally. Galaxies are distributed in the universe, not in a uniform way, but in this network-like structure where you have regions which are bright pink and purple here, where you have lots and lots of galaxies. And then you have the dark regions that have very few galaxies. We call those voids. And so in my research group, we do a lot of work trying to understand galaxies at the nodes where all this filamentary structure overlaps. That's where we can have the largest, most massive structures in the universe that we call galaxy clusters. And we want to understand how this unique environment can affect how galaxies form and how they evolve over time. So galaxy evolution is a fascinating subject in my very biased opinion, but it's also a really frustrating one. And that's because as observers, we can't actually observe galaxies evolving. And the reason for that is the timescales of all the physical processes that are important to galaxy evolution are much too slow. So they take millions or even billions of years to occur. And so that means we can't see a galaxy and watch it evolve over time. But we can still understand something about galaxy evolution. And there are two kind of complementary approaches to probing galaxy evolution observationally. One is to look at the fossil record. So this kind of research we sometimes call galactic archaeology. And the idea is to look at our own galaxy, the Milky Way, or other very nearby galaxies and study them in a lot of detail, places where we can even resolve individual stars and study the chemistry of individual stars. And we can try to understand what must have happened in the past to give us this fossil record that we see today. So that's one approach to studying galaxy evolution. And the other is to actually go back in time and to see galaxies in the past and understand how the population of galaxies must have changed over time. And so again, we can't see one galaxy evolve, but we can see galaxies at different epochs and figure out how on average galaxies evolve. And the reason we can do this is because telescopes are really time machines. And that's because light does not travel at infinite speed. The speed of light is finite. So when we look at objects in the night sky, we are looking back in time to what those objects look like in the past. So if the sun is shining where you are right now, that light was emitted from the surface of the sun about 8 minutes ago. When I'm looking at pictures of galaxies using telescopes like the Hubble Space Telescope, I'm looking at light that was emitted millions or even billions of years ago. So when we're looking at distant objects, we're seeing light that was emitted a long, long time ago. But this gives us some power to, let's say, go look at a bunch of galaxies that are 1 billion light years away. So we're seeing them like they were 1 billion years ago. And then you can do the same trick, but 2 billion light years away, 3 billion light years away. And then you can study the galaxies at these different epochs and figure out how, on average, the population of galaxies has evolved over time. So I would love to see one galaxy evolve. I can't, but I can do this. I can study galaxies at different epochs. And galaxy evolution is complicated. We're going to talk a little bit about some of the special things that happen in dense environments for the rest of the talk. But I wanted to divide galaxy evolution into kind of two rough categories. We have galaxy evolution that's driven by things that are internal to the galaxy. And that could be, does your galaxy have a very big black hole at its center? Again, very interesting topic. I don't have time to touch on today. Happy to take questions on. Do you have a big black hole that's giving lots of energetic feedback to your galaxy? Do you have a whole bunch of supernova explosions that have gone off recently? Things that are internal to the galaxy can rearrange the gas and the stars and make the galaxy look very different, cause galaxy evolution. You can also have things that are external, and that's where my research group is focused. And so we try to understand, how do the unique things that happen in dense parts of the universe affect galaxy evolution? And there are lots of observables we could study, lots of different properties of galaxies we can measure with all different telescopes. But today I'm going to mention two specific observables. One, the shape of galaxies that we call morphology, and the other is the rate at which galaxies form stars. And the reason why these two observables to me are really interesting to study is by studying these two things we can observe with telescopes, we can start to understand some of the physical processes driving galaxy evolution. So here's my schematic diagram showing these two measurables. On the y-axis, we have the rate at which galaxies form stars. So for the Milky Way, we have this huge galaxy with 100 billion stars. Our galaxy makes about 1 new star a year. So we're a star-forming galaxy, but only about 1 star a year. Some galaxies make way more than that, and some galaxies make almost no stars per year. So we have this variable on the y-axis, which is the star formation rate. And on the x-axis, I have the galaxy shape. So we talked about two shapes, blobby ellipticals and frisbee spirals. But you can actually make a continuous variable here on the x-axis that goes from pure disky spirals to pure 3-dimensional elliptical things. And in this space, in this plane, the vast majority of galaxies are either spirally blue star-forming galaxies or orangey red, not star-forming elliptical galaxies. But there are small populations that live off axis, and also the proportion of galaxies living in these different quadrants turns out to depend on the cosmic time. Is it today or is it 10 billion years in the past? And also it depends on the environment in which we find galaxies. So by measuring star formation rate and the shape of a galaxy, we can start to understand what's happening. And so underlying these two observables are a whole bunch of physical processes. We're not going to go over all of these today, but some basic ideas. If you want to move from being a disky spiral galaxy to a blobby elliptical galaxy, you can do that through merging. So if I take two spiral galaxies, nice disky rotating galaxies, and smash them together, everything gets randomized and I end up with a big blob. So merging of galaxies can move you from the left to the right. Star formation, the rate at which a galaxy forms stars, is dependent on how much gas it has. So if you've got lots of gas available for star formation, you're going to be star forming. So how might you shut off star formation? You could remove gas. And that turns out to be one of the primary things that we're studying right now in my research group, going from the top half of this diagram to the bottom half. And we call that quenching. So in the last part of today's talk, I'm going to talk specifically about one of the ways we can quench galaxies, going from star forming to not star forming. But as I mentioned, we're really interested in galaxy environments and the things that are special about being in dense environments. So one thing that can happen if you have nearby neighbors is you can have mergers. So I couldn't do this talk without showing a couple of beautiful images of merging galaxies, these spectacular pictures. This is again from the Hubble Space Telescope showing two interacting galaxies. And this happens not all the time, but it's also not rare. So here's a photo gallery of many, many interacting galaxies. So we have all different mergers captured at different epochs in the progression of their merger. But just like anything in galaxy evolution, there's the frustration that you cannot see a merger from beginning to end. It takes about 1 billion years. But although we can't see a single merger happen from start to finish, we can find different mergers at all different stages in their coalescence and understand what happens when galaxies merge. And it turns out what happens when galaxies are interacting strongly, and if they have a lot of gas, that can lead to a huge burst in star formation. So you can move up the y-axis in that previous diagram that I showed. So mergers are really interesting, fascinating examples of a dramatic way in which galaxies can rearrange their shape and their star formation rate. And just to note, a galaxy merger is also in our future. So we live in a spiral galaxy called the Milky Way. When you look up at the night sky, particularly in the summer here in the Northern Hemisphere, you can see what we call the Milky Way, which is a piece of our galaxy in the night sky. And if you are in somewhere with dark skies and you know where to look, you can see a little fuzzy patch on the sky, which is our nearest large neighbor. So another spiral galaxy nearby called Andromeda. And we are moving towards each other at very high speed. And so in a few billion years, these two galaxies, the Milky Way, our own, and Andromeda are going to merge. And so it's interesting to study galaxy mergers out there in the cosmos, also because it's the future of our own Milky Way. And so this is a bunch of panels, which are a simulated view of what the night sky is going to look like as Andromeda gets closer to us, or as we get closer to Andromeda, we're moving towards each other. And so our night sky would become much, much more dramatic. And the end product of the Milky Way and Andromeda colliding together is expected to be a giant elliptical galaxy. And so in billions of years' time, whatever beings may exist in the Milky Way, their night sky is going to look very different than our night sky today. So mergers are really important in rearranging the shapes, the colors, the star formation rates of galaxies. So mergers between two major galaxies is one important environment, but there are other environments in which we find galaxies. So galaxies can live kind of all on their own, without any large companions nearby. And the evolution of those kind of galaxies is really dominated by internal things. So again, black holes, supernovae, things that are inside the galaxy. If you have a collection of a few galaxies bound together by gravity, we call that a galaxy group. Turns out in this environment, you can get lots and lots of mergers. And then the most dramatic, the biggest, densest environment in which we find galaxies are collections of hundreds to even thousands of galaxies called a galaxy cluster. And most of the galaxies in a galaxy cluster are what we call red and dead. So if you look at that galaxy cluster right away, you can see it's dominated by these orange fuzzy blobs. It's not filled with spiral galaxies. And this is because we think there's some evolutionary processes that happen efficiently in dense environments. And that's the question that we're really trying to address in my group, is which processes are dominating the evolution of galaxies in this special environment. So many processes at play. Galaxies are complicated: stars, gas, dark matter, dust, interactions, lots and lots of possible ways that galaxies can merge. But here's a summary of a few of the things that are unique to living in a dense environment. So these are 5 separate physical processes. They probably all play a role, and our job as researchers is to understand which of these processes is most important and when and in which environments. So the top 3 highlighted in pink here are interactions between galaxies. So if you've got a group of galaxies or a cluster of galaxies, you've got galaxies living in close proximity and they can interact with each other. They can merge. We've seen that in our previous images. But also sometimes the galaxies are moving by each other so fast, they don't merge. And they can affect each other. And we can actually see this in the top left image. This is called the cartwheel galaxy. This galaxy was a nice normal spiral, and now it has this blue ring of star formation. And that was caused by a little galaxy flying by. And so if you have repeated flyby interactions, not mergers, you can change the shape and properties of a galaxy, and we call that harassment. You can also have tidal interactions. So galaxies are extended objects, which means the close side will feel more gravity than the far side, so they can get stretched out via tidal interactions. But in my group, we're really interested in the final 2 here, which are not interactions between galaxies, but are interactions between a galaxy and the rich cluster or group that it finds itself in. And so I'm going to just talk about these 2 mechanisms today. I'm going to finish with just a look at one of our current research projects. So here's a very simple schematic diagram of a galaxy. And in my group, we're really interested in galaxy quenching. So to understand how you shut off star formation, you need to understand how does star formation work in a galaxy in the first place. So here's my schematic of a galaxy. You've got the stellar disk. So imagine this is a nice spiral, disky, frisbee galaxy. We've got the stars we can see. And then beyond the stars a little bit, but still in a nice disk, we have cold gas. Stars, it turns out, form out of cold gas. If you don't have cold gas, you don't have star formation. And then within that, we have the galaxies embedded in a large structure called a dark matter halo. We're not talking about the dark matter today, but it turns out within that dark matter halo, we also have hot gas. And this is embedded in the cosmic structure, as we saw. So we have inflow of new material from the cosmic structure. And so gas inflows, it's pretty hot. Over time, it can eventually cool, make the cold gas. The cold gas can make the stars. That's a steady state galaxy. Galaxy happily continuing to form stars will look like this. So I'm interested in quenching what shuts off star formation in galaxies. And there's a couple of possibilities. One, you either shut off the cosmic supply of gas, or you somehow remove the hot gas altogether. So if you don't have that reservoir of hot gas to eventually cool, you're going to eventually run out of material from which to make stars. So you can keep forming stars for a while from whatever cold gas you have, but once you've used it up, you're done. So it turns out this takes 1 to 2 billion years or so, and we call this process starvation. And this can happen in galaxy clusters. A galaxy in a cluster is no longer out in the cosmic web as the center of its own gravitational potential. It stops having cosmic inflow, and so it cannot replenish its cold gas. So this happens, and this is interesting to study. But more dramatically, what can happen in a galaxy cluster, and what my group's really interested in right now, is understanding what if something even more dramatic happens, where you don't just shut off the supply of hot gas, you actually remove the cold gas from a galaxy. And so this is a process called ram pressure stripping. This happens. Here's an image. I apologize, I'm speeding up a bit. I know I'm starting to run low on time, and I want to get to just a couple of nice pictures to finish. So this is a picture of a galaxy, schematic of a galaxy falling into a galaxy cluster. When it does that, it feels a wind of all of this dense material it's moving through. And when it does that, the gas actually can be blown out of a galaxy. And here's a beautiful image of that on the right. The grayscale is the stars in this galaxy, and the contours on top are the gas, and you can see it being kind of blown out behind the galaxy here. So this is a ram pressure stripped galaxy, and we now have an abundance of beautiful images of these things. The most dramatic ones are called jellyfish galaxies. And here you can see the optical image of the galaxy, and then in pink here and in blue on the right, you can see the gas being blown out. So this is an image of the gas that you see in pink on the left and blue on the right. So these jellyfish galaxies happen, and I couldn't do this talk without showing you the most dramatic one I've ever seen. This is a galaxy moving through a galaxy cluster. The visible light from the nice stellar spiral galaxy looks normal, and behind it is this huge stream of gas that's flying out behind the galaxy. So in my research group, just the final thing I want to mention today is this project we've been doing, trying to identify these dramatic ram pressure stripped galaxies without directly imaging the gas. So in this previous image, you're seeing the gas in red here. This is dramatic. You see this image and you say, wow, this is a galaxy that's undergoing something really dramatic. The challenge is observing the gas is much harder than observing the stellar light in the visible. We have way more telescopes to see the visible light. And so in my group, we set out to see, could we use the visible light that we have for millions of galaxies to detect galaxies that are likely undergoing stripping? Do they look different? Are they asymmetric? Can we see maybe a little bit of tails even just in the stars without seeing the gas? And so one of my former PhD students set up a project where he created thumbnails of hundreds and hundreds of galaxies in galaxy clusters, and everybody in the group went through them one by one and tagged the ones that looked odd, that had asymmetries, that had signs of tails. And turns out that to do this, we used beautiful imaging from the Canada, France, Hawaii telescope. So this is the telescope here on top of Mauna Kea, jointly owned by Canada and France and Hawaii. And the reason why this telescope was so good for this project is you can see the top row of images come from this telescope. The bottom row come from a telescope which is used to do the largest survey ever of the night sky, the Sloan Digital Sky Survey. And CFHT, the data is so much better for identifying asymmetries, tails, strange structures. And so we've used the CFHT to identify interesting galaxies in the optical, which again we have for way more galaxies than these studies in the gas. And so bottom line is we found a bunch of galaxies that look like they have tails. These tails seem to point away from the centers of the clusters they're in, which is again, what you would expect, a galaxy falling in, the gas is going to be stripped behind it, and that's what we see. And for a small subset of these galaxies, we went out afterwards and looked for gas. And just to show you one example, here's a galaxy cluster. Here's in the white boxes some of the galaxies we identified as looking like they had optical features, visible features that looked weird. And when you point a radio telescope at them to see the gas, you can see gas tails here in the contours. So I apologize, that was a little quick, but I wanted to end with one of the dramatic things that happens to galaxies in galaxy clusters. They can have this stripping. So I'll just conclude by saying galaxies are complicated objects, many physical processes at play, but galaxies are not island universes. They interact, they can even merge with nearby galaxies. And finally, galaxies in the densest environments like clusters can undergo some unique processes that are special to that environment. And we're trying to understand exactly which of all those different processes dominate when and where in cosmic time. So thanks very much.
Thank you very much, Laura. That was wonderful. The analogies between my field, evolutionary biology, and your field are astounding. And hopefully I can come back to that in question period after the next talk. And in the meanwhile, we have a question for our audience. So we're going to put up a question just to keep the audience active while we prepare for our next speaker. So here's a question on the screen. Which galaxy transformation mechanism has the worst name? And you have a choice of those there. So take a moment. Hopefully you've made your choice. And in fact, all or none are the right answer, depending on your perspective, I suppose. And here are the results of that poll. And there will be a formal question period following the next talk. And in the meanwhile, if you do have any questions, either for the previous talk or the next talk, you can post them in the Q&A chat form at the bottom of your screens. We'll move ahead and I'll introduce the second speaker for the day. Miho Janvier is a space physicist at the Institut d'Astrophysique Spatiale, France. Her current work focuses on the understanding of when solar flares occur, how solar storms travel in space, and how they impact planetary environments in the solar system. Dr. Janvier, in the next presentation, will illuminate for us what it means to live in the neighborhood of an active star. Dr. Janvier.
Thank you. Just sound check. Can you hear me well? It's all good.
Perfect, and your screen is perfect.
Okay. Okay, great. Well, thank you so much for having me, and it's great to hear Laura Parker's talk about galaxies, because it's actually the thing that I studied when I was in my bachelor degrees. But we're gonna travel closer to home, and I'm going to talk about our magnificent star, which is the sun. And before I start, I wanted to kind of talk about some events that are happening at the moment. So from what I understand, there are some people tuning in from all around the world. And maybe some of you live in Europe or you live in Canada, but you have some European roots. And maybe you have heard that the European Space Agency is actually selecting astronauts. And that's something that I'm really, really excited about, and I really, really hope to see more female astronauts in the future. But the reason why I bring this up is because I was following up what was going on with the European Space Agency and what they were planning to do, and I found out that they were actually trying to get away from Earth, so not just on the International Space Station, but also orbiting around the moon with the Project Gateway. Possibly getting some European also landing on the moon, and whatnot, maybe in the future also lands humans on Mars, which I find really exciting. I don't think I would want to go to Mars personally, but I think it's really, really exciting. But before we get there, there's something that we need to know is that it's actually really dangerous to be in space and away from the Earth's protection. And we already did know that more than 50 years ago when we landed humans on the surface of the moon. This is a really beautiful shot of a lunar landing, a lunar walking, if I may say. But even then, the Apollo missions and the Apollo mission astronauts knew that there could be some major events in the form of solar flares. So this is a report that I found, it's dating back from the 70s, and you can see the mitigation or the rules, what to do in case a major solar flare happens. And I found that it was kind of interesting because even already in the 70s, we knew that the sun could be playing up, and we had to be prepared for that. And so, the sun, of course, gives us some light in all forms, in all wavelengths, from the visible light that we can see with our own eyes, all the way to X-rays and sometimes even gamma rays. But it also sends particle storms, which are the threats that we call when we call radiation, when we talk about radiation. And close to my heart is the winds and also the storms that are magnetized that come from the sun. And that's what I'm going to talk a little bit more about in the following. But just to go back a little bit quickly on the Apollo mission, it's not something to forget, really. I think when we went back to the data, what you can see here in the yellow boxes or the yellow lines, the vertical lines, they indicate the level of radiation from particles that were coming from the sun in between the different Apollo missions. So you can see the numbers of the Apollo missions at the top, from Apollo 7 to the last one, Apollo 17. And you can see that we were kind of lucky in a way, in the sense that some of the most important particle storms that happened in between missions and not on the missions themselves. I think the one that the one that happened between Apollo 16 and 17 could really have been fatal to astronauts if they had been on an extravehicular journey. So yeah, if we want to go to the moon, or if we want to go to Mars, I think that we really need to understand first our sun. So what is our sun? You may have this image of I don't like to say boring, but sometimes some of my friends say, well, what is to know about the sun is indeed a boring yellow or orangey ball of light. And it's much more than that. When you see it in visible light, you can already see some features, and you may have noticed here some kind of freckles on the surface of the sun. So we call sunspots. And this image is taken in visible light. So do not look at the sun directly with your own eyes, but if you were able to, you would see the sun in this light. So kind of yellowish or orangey. But sometimes you can actually see the sun directly with your eyes and discover that it's much more to just a yellow ball. This is a picture taken from Earth of a total solar eclipse. I'm not sure if any one of you have seen one. I had the luck to see one in Argentina 2 years ago. I wanted to see one in December. There was a total solar eclipse also in Argentina and Chile, but because of the pandemic, I wasn't able to go. But if you ever get to see one, I highly recommend you to witness one. And what's really incredible is when the moon starts to cover the surface of the sun, and when you reach totality, you see the glow of the crown, the atmosphere of the sun that we call the corona. And you can see that the corona is highly structured. It kind of looks like hair coming out from the poles of the sun. So you've got the North Pole and the South Pole, and near the equator, you've got this like kind of loops that are kind of streaming away. And these are actually the structures, the magnetic field that is filled by particles coming from the interior of the sun. So the sun's atmosphere actually blasts away particles in space constantly. And that's what we call the solar wind. And just to understand that there's really this connection between the sun and the planets of the solar system, where we all of us and all the planets of the solar system bathed in this stream, this constant stream of particles that we call the solar wind. And it actually fills up the whole solar system all the way to the frontiers of it. And that's what we call the heliosphere. So I like to call it a kind of a magnetic vessel in which we travel throughout the galaxy, the Milky Way galaxy, protected by this big magnetic field that the sun generates. So let's come back to our sun. This is, again, the sun in visible light. But if we could see the sun in other lights, so this is another, like I've covered up the sun in another filter, we would see what happens in this elusive, I would say, invisible light, except during total solar eclipse of the atmosphere of the sun. So just as a reminder, I wanted to show you a little graph of the light that is emitted from the sun. I talked a bit earlier about the visible light, which you can see is a really, really small portion of the whole electromagnetic spectrum. So what we call light is actually kind of a misnomer in the sense that it really covers a large range of waves, from radio waves all the way to X-rays as well as gamma rays. And the sun's atmosphere, funnily enough, it's one of the big mysteries of solar physics, is much, much hotter than the surface. And the surface, as you can see, is in the visible light, it's around 6,000 Kelvin. We talk about Kelvin, which around this level is basically, degree Celsius, so Kelvin is around the same. And the atmosphere gets hotter and hotter, which goes against the laws of thermodynamics. And we're really trying to understand why this is so. But the sun's atmosphere emits in ultraviolet light and X-rays mostly. However, most of this light is actually shielded from the Earth because of the Earth's atmosphere, so either absorbed or reflected, and we do not have the capability to see ultraviolet and X-rays from the surface of Earth. So this is why we need to be in space and to send spacecraft to look at the sun in this light. So this is a mosaic of different filters from one telescope that is called AIA on Solar Dynamics Observatory, a NASA mission that was launched in 2010. And we have spliced different slices of the filters that actually look at the whole sun in super high resolution. It's 4K. And in super high temporal resolution. So every 12 seconds, we take shots of the sun in all those different lights. So we have a lot of data and it's magnificent. And what I want to show you is that if you now look at the sun in this light, in this extreme ultraviolet, you start to see a whole completely other world that is not just this boring yellow surface. So I'm going to point some different things, but for example, what you can see that is kind of suspended above the surface of the sun, and here you see a giant arcade, is what we call prominences, which are large plasma structures that are kind of suspended in the sun's corona, the sun's atmosphere, and sometimes the structures are blasted away into space. This is another filter. So the previous one was more around 100,000 Kelvin. This one is around 1,000,000 Kelvin. And you can see that we can see a lot of different regions that are brightened. That's what we call active regions. And they tend to also accelerate particles. They are they are also streaming particles away into space. So there are a lot of things to study. To my delight, I have to say. And when I started looking at these pictures, more than 10 years ago, I was like, wow, this is like a giant laboratory in which we can study this matter that we call plasma. So basically this soup of electrons and ions. But of my interest is whenever you have active regions, so regions that have a lot of magnetic field, they tend to release a bit like a volcano on Earth, although instead of lava is this soup of ionized matter. And you have those events that we call a flare. And you're going to see an example here where a flare is basically spurting away this material, this sun's material, really into space. We're going to zoom out, and what this video shows is a composition of a video looking at the sun, but also other telescopes that are normally hiding, but you see them assembled together on the video. So coronagraph, which kind of reproduce a total solar eclipse by hiding the sun and looking at what is going away, what is moving away from the sun. And so we saw this giant cloud of material coming out from the sun, and that's what we call a coronal mass ejection, or what I like to call a space hurricane or a solar storm, because I find it a bit cooler when I talk to my friends and family about them. This is an accelerated video where you can see the storms blasting away from the sun. It's accelerated, so over a few weeks. And what is interesting is you may see this, it's going to loop again, but if you look carefully, there are going to be two small objects coming from the bottom of the video towards the sun. These are comets. And you're going to see also some, so these are not UFOs, I've been asked a few times. These are planets, and they tend to be really bright. So that's why they saturate the CCD detectors on our telescopes, but you can see them moving. And what I want you to understand is that when the sun is blasting away those clouds can actually go on the path. So the trajectory can be on a planet's trajectory as well. And so we have consequences of these coronal mass ejections on the planets of the solar system. So this is what we call space weather, is basically affecting the space environment of planets. So we know that the sun sends UV light, visible light, X-ray, radiation, energetic particles out as well. I talked about the solar winds. And you have those coronal mass ejections as well, that is parts, and that tend to drive the most important geomagnetic storms here on Earth. You also have other events. So I talked about the solar wind. Sometimes the solar wind, like on Earth, can become a little bit stronger, a bit of a, not necessarily a hurricane, but in between. And when you have this interaction between a strong wind and a slow wind, you will going to have some interaction regions that are also going to affect the space environment of planets. So not just Earth, but also Mars. You can see, and even here being recorded at Mars, as well as other planets of the solar system like Jupiter and Saturn. So with this, I really want to give you the feeling that the sun is not just this star that is in the middle of the solar system and has nothing really apart from giving us heat. It really is something that is living with us, and we're really living it and bathing in the solar wind, and sometimes being hit on straight on by solar storms. So luckily, the Earth is protected by a magnetic field. That's what we call the magnetosphere. It creates like a protective bubble. And you can see here the particles being deflected by this bubble. But sometimes this bubble is kind of shaken up by strong winds or by these solar storms. And there are a lot of consequences on our technologies. So not just in space, of course, our satellites, telecommunication systems, the GPS is affected, astronauts are affected, of course, but also here on Earth, and electricity grids can be affected by strong geomagnetic storms that have been, that are the consequences of those storms coming from the sun. And for our friends in Canada, maybe you've heard of this event that happened in the Quebec region, as well as the Northeast USA region in 1989, where a whole electricity grid was under shortage, was completely impacted because of a geomagnetic storm. We lost some satellites, so whether there was science satellites, communication satellites, so private communication satellites that happen as well. And sometimes, and that happened quite recently with Hurricane Irma in September 2017, what you can see in this video here, the red part is the blackouts in the radio emissions, in the radio wavelengths that we use for emergency radio communications. And so when you have a particle storm coming from the sun, that impacts, that impacts some certain regions of Earth where we fail to communicate with radio communications, and that happened during a solar storm. So we kind of call Hurricane Irma like the perfect storms, in the sense that it was a space storm as well as a terrestrial storm happening at the same time. So just to be aware that those kind of things can happen, and very close to home, really. So in my research group, what we're trying to do is and me particularly, I really like to understand what's the genesis of those storms. This is a numerical simulation on which I worked, which tried to reproduce this big magnetic field that is growing and erupting on the surface of the sun. And recently with my student and a collaborator, we are trying to now try to propagate this big magnetic field in space in order to understand how, well, first of all, how it propagates and how it impacts the planets of the solar system. So luckily for us, we have, this is a diagram that shows the sun and the earth. So it's a kind of a weird diagram in the sense that the earth is not moving and the sun is not either, but you can see different objects. You can see Mars, you can see Venus as well, which is here, and you have different objects which are different space missions that we have sent. Maybe you've heard of the Rosetta mission that went to see to visit a comet. We've got Messenger, a spacecraft that went to visit and to orbit around Mercury, Venus Express, and all these I like to call them little messengers in a way that humanity sends in the solar system can be impacted by solar storms, and they can record their arrival at those different locations in the heliosphere, the solar system. And so some of the projects that I've led was about how we can gather all this data and try to understand the generic shape of those storms, a bit like a hurricane. We kind of know from space what they look like. Can we know the shape of the solar storms in space? This is kind of the data. It's just to show you that sometimes data, it's not just pretty pictures. It can be just a time variation of some parameters. But just the one thing that I find interesting, and that's the reason why I put the Curiosity rover picture, is because even on the surface of Mars, these little robots, so in particular, Curiosity has a detector for radiation, and it can actually feel when a coronal mass ejection, a storm, is passing nearby Mars, because the amount of cosmic rays that are coming from the galaxy or outside of the galaxy is decreasing, because the storms are like giant screens for those cosmic rays. So again, I kind of like the fact that sometimes we feel, especially if Earth and Mars is really close by, we feel some consequences on Earth that we also know that a robot on the surface of Mars has also felt, which I blows my mind, I have to say. So recently we've sent we're getting closer to the sun. Literally, so we've sent 2 spacecraft, one in 2018, the Parker Solar Probe, the NASA mission, and Solar Orbiter last year, actually. So I got to see the launch, which was incredible. It was just before the pandemic. I think it's the only spacecraft that has been sent into space for which the commissioning, which is the time when we look at whether all the instruments are working fine, has been made from home, because we're all working from home. But it's a tremendous, it's a really exciting mission. You can see the boom here, where you have a lot of different instruments that are sensing the space around the spacecraft, and all the telescopes here that are shielded by the thermal shield, because we're really getting close to the sun. I'm going to finish just with just a list of instruments, but I wanted to show you this diagram here. That shows the Parker Solar Probe mission, Solar Orbiter. They're kind of like sister spacecraft. Parker Solar Probe is getting closer, but doesn't have any telescopes. And Solar Orbiter, if I go a little bit further in time, Solar Orbiter is going to get out of the ecliptic plane, which is the plane of the orbits of the planets of the solar system. And for the first time in human history, we're going to look at the poles of our sun. And that's really exciting, because we've done that for Jupiter and Saturn. So it's Saturn and Jupiter, and we found really interesting things. So I wonder what we're going to discover on the surface of the sun at the poles. I've got a few other things, but I'm going to leave you with this kind of exciting thing to look forward to in the next coming years. Thank you so much for your attention.
Thank you very much, Miho. That was wonderful. We have a question that was posed by Miho for the audience, which we will show on the screen, and then we will use that to segue to the question period for both our speakers, Dr. Parker and Dr. Janvier. And thank you also, Miho, for linking the names of the two talks with the Parker orbiter and our first speaker having a last name of Parker.
That wasn't intended.
The question is now on the screen. Is the atmosphere of the sun hotter or colder than its core? And we'll show the results of that poll in a moment, and then we will head to the question period. We probably have time for 2 questions from each speaker. We might run just a few minutes over time. And there are the results of the poll. Okay, so we can run into the question period for our first 2 speakers, and I guess we can go in the same order that they presented their talks. The first question for Dr. Parker comes from Waterloo, Ontario, and it asks about the facilities that are used. You hinted about one facility and whether you travel for collecting data.
That's a great question. Thanks, Ed. So actually, I know Ed from Waterdown because he's really active in the local amateur astronomy scene with the Royal Astronomical Society of Canada. So I use as many telescopes as I can get time on. So that includes ground-based telescopes in Hawaii and in Chile, and also space-based observatories. So I'm a multi-wavelength astronomer. I use visible telescopes like the one I showed, CFHT, like the Gemini telescope, like Hubble, but also radio telescopes like the ALMA Observatory in Chile. So I use lots, depending on the science question, that dictates where we apply for telescope time. When I started out as a grad student, I used to go visit these places to do my observations. These days, most of them are done remotely. So you're at home and there are people at the observatory taking the data. And the next morning you get an email saying, congratulations, we collected some great data for you. And here's a link to where you can find it. So unfortunately, these days, the graduate students don't get to travel as much as I did. But of course, for climate reasons, that's a big plus, that we can stay home and have the data collected in these remote observatories and then sent to us.
Thank you very much. And parallel question also from Waterloo, from Ed, for Dr. Janvier, and it has to do with, should we worry about communication breakdown here on Earth because of such events?
Yeah, so I wouldn't say worry in the sense that there are so many other things that can happen, around the world. But I would say that yes, we have to be prepared. And actually, some countries, such as the US or the UK, do have mitigation systems in place, and they also have prediction systems in place with NOAA in the US or the Met Office in the UK. So this is something that we're really working towards. So better scientific understanding, of course, but also a better mitigation process. So as an individual, I wouldn't say worry, but yes, advocate for it whenever you can.
And while you're on the screen, there was a question about what is the answer to the question that you posed for the audience? Is the core hotter?
Yes,
or
I didn't give an answer when I asked the question, but it's a tricky one because it's actually slightly colder on average because the core is around 15 million and the atmosphere is around 1 million. But sometimes the atmosphere can actually get really hot, up to 15 million degrees. So the fact that you all answer like 50-50 is I'm happy with your reaction.
Okay, question for Dr. Parker. This comes from another part of Earth, Nepal, and it has to do with the gases that are blown out. Do they contain organics?
So the gas that gets removed from galaxies, most of the gas in galaxies is predominantly hydrogen. Like most things in the universe on large scales, we're dominated by the simplest things in the periodic table. So most of the gas is hydrogen, a little bit is helium, and tiny bits of other material. So carbon and oxygen atoms, which I apologize if there's any chemists in the audience. In astronomy, we call everything beyond helium a metal. And that's because they can help the cooling of gas in nature. But in short, most of it's hydrogen and helium, a little bit of other stuff, which could include some very, very small amounts, tiny small amount of organics. But to first order, it's hydrogen.
Thank you very much. And a question back to Dr. Janvier. The dramatic video that you showed with the space hurricane, as you described it, people wonder what time scale and what spatial scale was involved. I think you hinted at with one of the other videos, but
yeah. So the spatial scale. So if you look at the storm at the beginning when it's being formed on the sun, it can actually reach a quarter of the sun. But I don't know whether you remember this video where we were zooming out from the sun and looking at what happens after. Basically, what happens is that this magnetic field is it's not really constrained anymore, because the magnetic field decreases as you go away from the sun, and it expands and expands and expands to the point that as it reaches the Earth, the spatial scale is basically the size of the Sun-Earth distance. So quite a large scale. And in terms of time scale, it depends from one event to another one. It depends on how much energy it has. It's a bit like when a volcano explodes, does it explode like kind of, is it like just lava flowing out, or is it just a big burst? But generally it's in between a few days from the sun to Earth, if the Earth is on the path, to a few hours for the most I would say the most energetic ones, so the ones that have a lot of kinetic energy.
Thank you very much. So the remaining questions, we do have a second question period later, a panel discussion. So we will reserve some of the questions for that, and we will move on in our program to our third presenter for the morning. So I will now introduce Françoise Combes, is a professor in the College of France on the chair Galaxies and Cosmology. She is an astrophysicist at Paris Observatory and member of the Academy of Science. Her main areas of research are the formation and evolution of galaxies, their dynamics and coevolution with supermassive black holes, the interstellar medium of galaxies, and dark matter models. Dr. Combes will combine those elements to provide for us a description on the history and content of the universe. We're very honored to have Dr. Françoise Combes.
Thank you very much. Oh, sorry. I'm trying to come back to my, sorry about that. Sorry, I had a problem, a little problem.
No worries.
Okay. So now I'm just sharing the screen again. Okay, so I guess you see the screen now.
Perfect.
Okay, and I will just come to the main. Okay, so my speech today will be the history of the universe, and I will take the history in the sense of what is happening to the universe, not only from the Big Bang to today, but also how the knowledge of the Big Bang has been known for the scientific way, history of science. So you see that from the beginning, all the astronomers wanted to, are very curious, they wanted to know what is behind this sphere of the celestial sphere here. There's a beautiful image of Camille Flammarion. And now we know, of course, much more than that, and we know until the multiverse. I will try to go to that. So in the old times, until the 20th century, in fact, we had some metaphysics, in fact, not really science. We knew only what happens in the very nearby universe, that is the first, the Earth, and then the solar system, and then the galaxy. In the beginning, there was mythologies like this, Hindu, China, when they thought that the Earth was flat. Of course, it's the first view that we have from Earth. And curiously, they imagined that the giant turtle was bearing this, maybe sometimes was elephant or snake. There was also a northern mythology with a cosmic tree. And very interestingly, in the recent time in Germany, we discovered this disk of Nebra, which come back to 1600 years before Christ. And all these people were observing the sky very attentively. They were the moon, but also you see 7 stars that could look like the Pleiades. But if we jump now to the 18th century, people, of course, continued to observe the sky. And there was this Charles Messier, astronomer in Paris Observatory. And he was stricken by the discovery of comets, and in particular, the Halley comets that Halley predicted in the beginning of the 18th century to come back 76 years after its first discovery. And indeed, it came back in 1758. And Charles Messier, who was a young astronomer, was really impressed by that. And he made a catalog of the sky of nebulous objects, not only stars, which are point sources, but nebulous. And you see there was more than 100 objects in the Charles Messier catalog that we still use today. But he didn't know what all these nebulous objects were. And in fact, when you see here Messier there was many objects. There was some, the Messier 1, that it is exactly the nebulous of the crab. It's a supernovae, an envelope of the star which has exploded in year 1000. And you can see also globular clusters, a lot of stars together, 100,000 of stars in a small volume. You can have a planetary nebula. What a planetary nebula is just the end of the sun, for instance, the envelope of the sun which explode. But you have also galaxies. And Messier 51, for instance, very well known, is a galaxy. You can have also a nebula in the Milky Way, which like Orion Nebulae, which makes stars. And curiously, people did not know that galaxies exist until 1920. In 1920, there was a great debate between two clowns. There was one with Harlow Shapley, that was a leader, and Herbert Curtis. And Shapley thought that the Milky Way, our own galaxy, was very, very big, and all the universe was the Milky Way. All the nebulae were included in our Milky Way, while Herbert Curtis thought that some nebulae were outside the galaxies, and there existed other universes, other galaxies. And why we were not able to give an answer at that time is because we didn't know the distances, in fact. Here you see what were known in this beginning of the 20th century. There was a Slipher, Vestor Slipher, that was looking at spectra of this nebulae. And this nebulae had lines of hydrogen, and the spectral lines. And spectral lines, when they are redshifted or blue shifted, you can, by Doppler effect, measure the velocities. And the velocities of these nebulae were very high. In fact, several thousand kilometers per second. People did not understand that at this epoch. There was a captain, an astronomer at Groningen, who was observing the Milky Way and a lot of stars. And he had a good idea to say, well, all the weak stars are farther away, and maybe most stars are about the same luminosity, and those who are weak for us are very far away, and the strongest one are closer. So he made a map of the galaxy, and of course the sun was in the center. Again, we always think that we're at the center of the universe, and you know that after the Copernic revolution, we knew that the Earth is not at the center, but the sun is at the center, the Earth is rotating around the sun. Again, for the Milky Way, we did the same error. The sun was at the center of the Milky Way. And why? Because in fact, he forgot to take into account that there was obscuration by dust. In between stars, there was a lot of dust, grains of carbon, silicium, and so on, that absorb the light from the stars. And it's like this image that I show at the left here. When you are at night, you have a light, and you are always at the center of the light. So you see only in a circle around. And here, because of the dust, you see only the nearby stars. And at this epoch, also Cornelius Easton was making a map of our own galaxy. He saw some agglomeration like a spiral arm. So you see the spiral arms were there, but the sun was still at the center of the galaxy. So the spiral structure was very weird. And the progress was given here when we knew how to measure the distances, because if we have no distances, all the objects appear on the sphere, celestial sphere, at the same distance. And one big progress was done by Henrietta Leavitt, that you see her here. And she was working in an observatory to observe stars, and she noticed that there was a lot of stars variable. She observed about 1,000 or 2,000 variable stars, and she noticed that there were some stars called Cepheids, because they were in the constellation of Cepheids, that were varying, and varying about a few days. And at some time they were very big and very bright, and then sometimes they were contracting. So they were oscillating like that, contracting and expanding. And their period, which is independent of distance, of course, the period was proportional to the luminosity, intrinsic luminosity. So this gives you a distance indicator, because when you have a apparent luminosity from the period, you can deduce the intrinsic luminosity, and you have the distance. But at this epoch, well, it was 1909, but it was not believed by all astronomers. And for instance, Harlow Shapley did not believe it. Herbert Curtis, yes, but not Shapley. And that's why he was still believing that the Milky Way had 100 kiloparsec. Kiloparsec means the parsec is 3 light years. So you imagine 300,000 light years, while for Curtis, it was 10 times less. And well, at least Shapley was wrong on this, but he was right on the point that the sun was not at the center of the Milky Way. And he had the good idea to have the map of the globular clusters, which map all the halo of the Milky Way. And of course, the globular center clusters were not in the sun, but in the galactic center. So he was the first to see that the sun is not at the center. And we know now that we are a little bit aside from the center of the Milky Way. And indeed, this is exactly the point of position. So the end of the debate was given by Edwin Hubble, who was looking also at the velocities of the galaxies, the nebulae, but he had discovered in 1925 and 26 Cepheids in what we call Messier 31 or Messier 33, nebulae from Charles Messier, but it was galaxies. And he, because of this distance indicator, he could determine that these were really very far away, could not be inside the Milky Way, and they were indeed independent galaxies. So the proof was given that galaxies exist, and our universe is much bigger than was thought before. At least it was including nearby galaxies. And in 1929, he discovered that there was a proportionality factor between the velocities that are apparent. Galaxies are recessing from us, and their velocity is proportional to their distance. So he also discovered another way to indicate the distance. And what we know now is that this was the beginning of the universe in expansion, and it was both Hubble and Lemaitre. Georges Lemaitre was a Belgian priest, in fact, a very fan of astronomy, and he also recognized that the expansion of the universe was not really that all galaxies was recessing from us, because the velocity was very, very fast. And now we know that if we keep this interpretation, we will see some galaxies going much faster than the velocity of light, which cannot be. But Georges Lemaitre at this epoch noticed that it was the space that was in dilatation, expanding. So there is a redshift, like a Doppler effect, but it is not a Doppler effect. Only space is in dilatation, expanding like this balloon, while the space is the surface of the balloon, and you see the galaxies are not moving, but they seem to be farther and farther away from each other because of the space that is expanding, and there is a proportionality between their distance and their apparent velocity. You see here a photon. When the space is in expanding, the photon is also expanding, and the wavelength of the photon is larger, so it's redder. And this is the redshift that is now an indicator of distance. So, but let's come back. In fact, the theory was also progressing in the same time as observation. And at this time, at 1905, you had the special relativity invited by Einstein. And in 1915, about the same epoch, you have the general relativity, meaning that the gravitation is not a force like the other forces, like electromagnetic force, but it is a space distortion, like this little cartoon here, where space is a 2D, to me more easy to represent. And you see that there's like a carpet here, and all the bodies, massive bodies like the sun, you can imagine that this blue point is the sun, is making a distortion of the space. And of course, all the photons and also all massive bodies will tend to be deviated by this distortion. And this is the gravity. So when Einstein wrote this equation was relating the geometry of this universe, deformation, to all the mass and energy which is in the universe. And he tries to solve this equation, and he found that either the universe was in expansion or in contraction. And at this epoch, 1917, you had not yet discovered the expansion of the universe, so he wanted to have a static universe, very stable, because it was the idea at this epoch. The universe is only stable. So he added a constant, lambda, to his equations and saying, well, it's not very beautiful, but it is a necessity if you want to have a static universe. It ruins the beauty of the theory, but it is there. And then, of course, in 1929 and 30, we discovered that he was wrong, because the space is in expansion and the velocity is proportional to the distance. Georges Lemaitre was the first to not interpret like these velocities by a Doppler effect, by an expansion of the universe. And coming back, looking back in time, he said, well, if the universe is in expansion, it means that in the past, it should have been very dense and hot. So he imagined that there was a primordial atoms, a very, very small universe in the beginning. And this, of course, we know now it is called the Big Bang, the first explosion, but this was not accepted at this epoch. You know, even Fred Hoyle, who was a very distinguished astronomer in the UK, he was giving talks at the BBC, outreach talks. In 1949, he was completely not believing this Big Bang. So he gave this Big Bang like to make fun of it, to put this in derision. He called Big Bang. And finally, this name has remained until today. And there was proof of this. And you know that in 1965, there was a serendipitous discovery of the radiation, the vestige, fossil radiation of the Big Bang, that was discovered by Robert Wilson and Arno Penzias, these two people here. These two people working for Bell Telephone Laboratories. So this was applied research. In fact, they wanted to know if it was possible by radio waves, radio in the millimeter range, the wavelength is millimeter, and they had a telescope, which was this horn in behind there, and with this horn, they were sending signal to satellites. They wanted to know if it was possible to communicate with artificial satellites and coming back to Earth to communicate to several points in the Earth by this telecommunication. And their experiments were really annoyed by this noise, a very strong background noise that had no origin. They thought that first it was the sun, but at night it was the same. Maybe the Milky Way, the galaxy, but no, it was not. When the galaxy went up and down, it was exactly the same noise. So it's a noise that is everywhere. There is no origin. And we know now it is really the vestige of the Big Bang coming from the last surface of scattering, and it is everywhere. And the number of photons that you have from the Big Bang is 400 photons per cubic centimeter now. So since these photons go with the velocity of light, there is 10 to the 13, that means 10,000 billions of photons per square centimeter per second that crossing you in this moment. So it's impressive. And when you look at all the background in the energy, new frequency and the flux, you see that the background CMB, cosmic background radiation here, is dominating all backgrounds. the optical background, infrared background. All these backgrounds are due to all the stars and all the galaxies radiating in the universe. And they are 1% only on the Big Bang background. So it's a very huge background. So where are the photons coming from? In fact, they are coming from the last scattering surface. And this, I put this analogy from the sun, from the previous talk. In fact, it's very well introduced here, is that when you look at the sun, you see only the surface, because all the photons in the sun, there are a lot of scattering, billions of scattering, and it comes out only when it becomes optically thin to scattering. Here, you see only the surface. And all the sun you see is coming, all the photons are coming only from the last scattering surface. It's the same for the Big Bang, in fact. The Big Bang becomes opaque at the beginning, and then it is optically thin. So what you see, and there are 3 satellites that have come and have been launched, COBE in the 1992, WMAP in 2000, and Planck 2013, that have been launched in the sky to see all the sky in this millimeter wavelengths, where you see the cosmic vestige of the Big Bang. And what you see is constant. In fact, it's like a mist. If you have eyes possible to see this radiation, you see nothing. But if you subtract this constant, and then you begin to see this, this is all the sky in some reference frame here, and you see that it is hotter in one side and colder inside. Hotter when it is red and colder in blue. And this dipole is due to the fact that our galaxy is moving with respect to this cosmic background, and it is moving at 600 kilometers per second. We know that it is local motion, which is attracted by galaxy clusters, super attractor, we call it, but it is only a cluster of galaxies that are attracting us. And when you subtract this dipole, and of course you see this, which is the emission of the Milky Way. We are in latitude and longitude of the Milky Way. Here the Milky Way is there. And of course, the Milky Way is radiating in millimeter wavelengths, where have some dust, that is, have thermal radiation, you have synchrotron radiation, plenty of radiation, but you have radiation where with a spectrum which has not the same slope and the same shape as the black body of the Big Bang. So you can subtract it because you have several frequencies. And when you have subtracted this, which is the foreground, then you have exactly the surface of the Big Bang, which is when the radiation is becoming opaque, and it is 300,000 years after the zero instant, the Big Bang. And this is the surface that we see. And what we see here is fluctuation. This fluctuation is very small. Respect to the radiation is 1 for 100,000, 10 to the minus 5. And these are the fluctuations, initial fluctuation, that will become the galaxies and all the structure in the universe. And all these map that we see in the cosmic background here gives you a lot of information of our universe, on the fate of the universe. The fate of our universe is synthesized here. You have, as a function of time, you have the size of the universe. You know that the universe is expanding. We are here now, and the possibilities, depending on the amount of density and energy that is in the universe, you could have a big crunch like this, or an infinite expansion. And in fact, we know that now we are in an infinite expansion. We are beginning an exponential expansion there, and the different possibilities were there in theory. If you had a large density, and a large density meaning larger than a critical one, you see the critical one is very small. It's 10 to the minus 29 gram per cubic centimeter. It's very, very small. But even if you have a larger density than that, then you have a finite universe, which has a positive curvature like this, symbolized by the sphere, but the universe is a 2D representation here. If you have a very small density universe, you will have a negative curvature. And if you have exactly the critical, you will have a flat universe. And all these observations of the cosmic background radiation that give us this answer that we are in a flat universe. And how is it possible to know that? Flat universe means that all the photons or the lights is traveling from the Big Bang to us in a straight line. And this is possible when you look at the map of the last Planck satellite here of the fluctuations coming from the Big Bang. You see that we have big fluctuation, you have small fluctuation, and you can plot here a number of fluctuation as a function of their size in angular size. Here you have 1 degree, 90 degree, you have small, only 1 or 2, which has big sizes. You have many, we have 1 degree, and then it goes down for the very, very small size perturbation here. And this, we know what it is this, because all these fluctuations are due to oscillation that we have between the radiation, the photons, and the ordinary matter, which is protons and neutrons at the beginning of the universe. So they are just making oscillation, dancing. And the first one is what we call the sound horizon here. And we know exactly this in intrinsic size, which is the ruler here. And since we are looking at this ruler with a certain angle, here it's 1 degree, we can know if the angle is here, we know that the curvature will be negative. If the angle is 1 degree, it is flat. If it is smaller, if it is larger than 1 degree, it will be open universe. So you see that the position of this peak gives you the curvature of the universe. And it is very well determined because the error bars of this point, you don't see it since they are very, very small. So we have determined exactly that our universe is flat. So the geometry of the universe is flat. So all these fluctuations that you see here are like a fingerprint, in fact, and I make the analogy here that from this fingerprint, you can measure the position of this, you can measure the height of this peak, the second peak, and so on. And from all this, I will not enter into the detail, we have been able to determine all the parameters of the universe. That is the density of the ordinary matter that we call baryons, the protons and neutrons or baryons. You have also the dark matter that Laura Parker has introduced to you. We don't know what are the particles of this dark matter, but we know that they are not ordinary matter. They are not protons and neutrons. They are not hydrogen, but some bizarre and exotic particles. We know what is density. We know that there is also dark energy and so on. Now, if I come back a little bit from the history, you saw that there was an astronomer in 1917, which was a real pioneer, Wilhelm de Sitter, that you see here. And he was trying to solve the Einstein equation with using the lambda that was introduced by Einstein to have a static universe. And he said, well, maybe it's easier to solve the equation if there is no matter. There is only lambda and no matter. And indeed, he found that there was an expansion and it becomes exponential, and is exactly the model that we are in now. Our model of universe that is observed by Planck and other observations is exactly the model of de Sitter. But of course, at this epoch, Einstein was making fun of it and say, well, your model exploded. And there was a cartoon here to make his model in the region. There was also other people like Friedman here and Georges Lemaitre that I have already introduced you, the Belgian priest here. And he was solving this equation and finding something in expansion, which was more compatible with the observation at this epoch. But of course, they had not the lambda. Lambda came afterwards. And in 1931, when Einstein realized that there was indeed an expansion of space, he thought that lambda, this constant that he has introduced, was not useful anymore. And during all the 20th century, this lambda was forgotten because Einstein said, well, it's not useful anymore. And we had no observation to prove that we need this lambda, so it was ignored. And as there was also some very peculiar, picturesque astronomer, George Gamow, who was an actor in this field of the Big Bang, who was saying that indeed Einstein recognized his biggest blunder. In fact, when you look at the history of science, maybe Einstein has never said that in that words. Mario Livio doubts this. He has written a book like this. But at least Gamow had a great sense of humor. He was the first that realized that we need a Big Bang. And he was believing in this Big Bang because of the formation of the light element like helium, deuterium, that you cannot form in stars. In fact, in stars, you destroy the deuterium. You form a little bit of helium, yes, but it is negligible with respect to all the helium that was formed in the Big Bang. In the Big Bang, it's so hot that you have a lot of nuclear reaction that form in mass, 25% in mass of the universe is helium. And this was only done in the Big Bang. This was written in this paper with his student Ralph Alpha, and he had the idea to add as a quarter, Hans Bethe, who had done nothing, but just to make alpha, beta, gamma in this paper. And this paper was published on the 1st of April. So this is really a good humor. Well, in fact, when we know now that this lambda is important, I will come back and anticipate a little bit. Einstein had introduced this constant lambda to have a static universe, as we have described. And this lambda was a function of the radius of the universe. The universe of Einstein was finite, constant, static, and the radius of the universe was a function of this lambda. And lambda was like an energy in the vacuum. And at the beginning of the 20th century, there was a large progress also of quantum mechanics. There was Wolfgang Pauli here that in 1920 has the idea to say, well, maybe we can make a link between this lambda, the energy of the vacuum of the universe, and the quantum mechanics that pretends that even if you have no matter, nothing, you have a residual energy, which we call the energy of the vacuum. And he's tried to sum that in the whole universe. For that, you sum all the ground state of all the degrees of freedom. You sum all this, and what he found is that lambda is very, very high. And since the radius of the universe is inversely proportional to its lambda, the universe of Einstein had only 31 kilometer radius. It's very strange. So he abandoned the idea, but people take this idea again in 1960s and 70s, where we discovered that there was quarks, in fact. There was a lot of progress in the theory. Now you have colors, you have the chromodynamic, the quantum chromodynamics of this theory, field theory. And then you can again, differently from in 1920, you can again sum the degrees of freedom of all the quantic field. And what you find, and this now they don't speak of the density of the universe, which is, as we mentioned, very low, 10 to the minus 29. They speak in energy. You know that energy E equal mc squared. So mass and energy are equivalent. So you can express its energy here, or mass, in GeV, giga electron volt. So let's take this unit. You have this 10 to the minus 47, which is exactly the lambda, which is measured by astronomers. And when you try to make the link with quantum mechanics, then you have either 2 10 to the 9 or 10 to the 72, which means that you have 10 to the 56 times more than is observed, or 10 to the 119 more than is observed. So it's completely wrong. So we don't understand still now why there is no link, in fact, or we don't understand quantum mechanics explain or extrapolate to the universe. And we don't understand what is this dark energy which is in the universe and which is corresponding to 70% of the energy of the universe. In fact, is this quantum mechanics energy real? In fact, it is. We know that there is a Casimir effect from a physicist called Casimir here. In between two plates, two metal plates here, we know that there is virtual photons, which is the origin of this energy of the vacuum. And inside the plates, you have less photons because you have only those photons that resonate at the border of the plates. That is the number of photons is proportional to delta X here. So you have less energy and you have a force between these two plates. And this force is measured. Indeed, we have this energy of vacuum. This is an evidence in the laboratory. So when in the 1998, all these people discovered that there was an acceleration of expansion, this was a right shock, in fact. Because in fact, until the end of the 20th century, we thought that the expansion of the universe was only decelerated, quite decelerated, because in fact, you have only mass in the universe, gravity, either ordinary matter or exotic matter, but mass. And mass has a gravity which is retaining the universe. So the universe is expanding, but it must be slowed down by gravity. Here, these people, these two groups, we got the Nobel Prize in 2011, were discovered by another indicator of distance, much stronger than Cepheids, but something like that, supernovae of type 1a. These supernovae are an explosion also, and there is light curve that goes up and then down, and the period is about 1 month or so. So they linked the period 1 month to the intrinsic luminosity of the supernovae. So that again, you can have an indicator of distance, but the Cepheids went only to nearby galaxies. Here you can go to the half of the universe, so it's much farther away. And when they determined the distance of the supernovae, and they had also the redshift, that is the distance from the expansion, and this did not match at all. The supernovae were much farther away than expected from the expansion. So the conclusion was that the expansion is really accelerated. And to be accelerated, you need a repulsive force, which was not due to the mass, the gravity. So you needed energy, and this energy is able to give you the repulsive force to accelerate the universe. So now we know exactly, with very high precision, the content of the universe. The content of the universe is first ordinary matter, which is mainly hydrogen, and 5% only of the total. It's what we call baryons, protons, neutrons, hydrogen, and so on, 5%. And the dark matter, which is exotic, made of particles that we still don't know the nature, is non-baryonic, and it's 25%. And all the rest, 70%, is the dark energy. We don't know at all what is this dark energy. The only thing we know is that we need it to accelerate the expansion and to make this lambda of the model of Willem de Sitter that is exponentially accelerating. Now I talk about the dark matter. I will just make a few slides about this because it is the content of the universe. It's very important, and still we don't know what it is. So it's important to make some what we know about the dark matter, at least to understand better the content of the universe. Well, this dark matter was already determined. The existence was suspected by Fritz Zwicky in 1937. Why? Because he looked at a coma cluster, a cluster of galaxies. You see here some galaxies. There is about thousands of galaxies. And he was able to make the spectrum and to see the redshift of the spectrum. So the velocities of galaxies with respect to one another was high, 1,000 kilometers per second. These are really true velocities. And to compensate this kinetic energy, you needed a lot of mass to retain these galaxies, unless the coma cluster will be completely dissociated. And for this, you needed 100 times more than the visible mass that you see in galaxy, 100 times more. It's really a lot, much more than the uncertainties you had on the mass. So he was suspecting that there is dark matter either in galaxies or in between galaxies, or maybe you had to change the Newton's law. After all, we don't know if the gravity law that we know on Earth is also valid for clusters of galaxies. Jan Oort also had the same kind of suspicions in the Milky Way. Maybe also Poincaré in 1906, he was just suspicious about the possibility to have dark stars, in fact, in the Milky Way. There was some stars that are shining, But after the star is dead, maybe you have a lot of dark stars that are circling in space along the Milky Way. And since in some cases he needed a lot of more mass in the Milky Way, he was suspecting dark matter. And in the rotation curve of galaxies, also, when you look at spiral galaxies that you have seen with Laura Parker talk, you see that galaxies are rotating like a disk, and they are rotating rather fast. Stars, gas are rotating rather fast. You can plot, when you have a spectra of all this matter, as a function of radius from the center of the galaxy, you can plot the velocity. And this was done by Vera Rubin in the 70s and other people after that. And she noticed that instead of going down, and even you expect a square root of radius, like a Kepler disk, like the planets around the solar system, but they were not Keplerian at all. And some galaxies were completely flat. So meaning that there are still more mass to explain why you have so much centrifugal force. To retain these stars and matter, you need a lot of mass. And this was determining the existence of dark matter inside each galaxy, not only in galaxy clusters. And what are the possibility for this dark matter? In fact, we know from Gamow and the nucleosynthesis of helium and deuterium that we cannot have more than 5% of protons and neutrons, because if we had more, you will have different abundance of helium and deuterium, and it is not observed. So we know that we have only 5% of ordinary matter. If we want to have 25% of dark matter, it cannot be baryons. So the hypothesis where maybe it's neutrinos, because at this epoch we knew that neutrinos, and normal neutrinos, could have mass, but now we know that they are very, very small mass and they cannot be dark matter. But at this epoch, we also know when making some simulations of the evolution of structure in the universe, that if you have a hot dark matter like neutrinos, neutrinos are called hot. Why? Because they are relativistic. They are very small mass. And when the structure form at the beginning of the universe, they have the velocity of light almost. So if they have the velocity of light, they make the pressure on the structure, and all the small scale structure don't form. So you have a universe which only large scale structure like this. When you have big, massive particles, then you can call them cold because they are not relativistic at all, and they don't prevent the formation of small scale structure like this. So this is three cases of simulation with cold dark matter, warm dark matter, and hot. And you see that what we observed in the universe is more cold or warm, but not hot. So this hot model was already ruled out at the beginning. And these WIMPs, which are weakly interactive massive particles, that were the best candidates from 1985 until now. They were neutralinos, supposed to be supersymmetric particles, but unfortunately, where they were supposed to be 100 times the mass of the protons, but unfortunately, we have not seen in accelerators like CERN, like a Large Hadron Collider, we have not seen any supersymmetric particle, and we have not seen any particle like the neutrinos. We have passed the energy where the accelerator could have produced this particle, and no particle like this have been produced. So we are really at a loss. Now we have no very good candidates for dark matter. Maybe it's a sterile neutrinos, which are completely elusive. We know that neutrinos is difficult to detect, but they are active. They interact with the rest of the matter. But the sterile neutrinos that have been postulated, we don't know if they exist or not, but they are not interacting at all. So they would be a warm dark matter. We could have also self-interacting dark matter. We can have, there are still a few candidates, and some are actions. That means particles that are bosons, that is, they can accumulate together like make a soliton, and which are really quantum particles. So they are making some fluctuation, like a fluctuation of quantum fluctuation. Here are some simulation of galaxies with this kind of dark matter, which is a big quantum particles. You have at the core, you have a soliton, and then at the galaxy, you see how fluctuating this particle are. This is dark matter by action. And you see that in between galaxies, you have filaments. And again, you have fluctuation. And we think we are trying now to simulate that and to try to make it compatible with observation. But it is difficult because in observation, you don't have so many fluctuations. So this is the state of the art in trying to find candidates particles, but there is also another solution for the dark matter, is that you change the law of gravity. This was proposed already by Milgram in 1983, when it was realized that indeed the dark matter is made of exotic particles. And of course, this dark matter evidence you have only by gravity. That is in the outer parts of galaxies, in between galaxies and so on. And you have no way to look, to observe this dark matter, which is not radiating, which is not absorbing light and nothing. So either there is a degeneracy here. Either you say that the gravity is Newtonian or Einsteinian, and then you postulate that there is a new particle. Or if you don't find this new particle, you can also say that at large scale or at low acceleration, weak gravity field, you have a different law of gravitation. And this is exactly what is the hypothesis here. And the hypothesis is that you change only when you have a weak field. The acceleration is 10 to the minus 11 times the field of gravity that you have on Earth. So it's very, very small. So in all the solar system, you have the normal Newtonian gravity, and you can only test at the border of the Milky Way. So it's only astronomers that can test this gravity. And indeed, when you look at the need of dark matter, the dynamical mass of the system, for instance, a galaxy or cluster of galaxies, with respect to the visible mass, when you have a strong gravity, you have no difference. You don't need dark matter. You need dark matter more and more when you have a weak field. And this is one of the theories. There are many theories now that are worked out. For instance, Einstein ether, which means that they are also making the same computation as Einstein, covariant theories with a tensor. But Einstein has a tensor but no vector field. So people are adding the vector field, which is a revival of the 19th century ether. You know that history is an eternal rebeginning. And this is still in work in progress. And we have some observation to test these theories. For instance, we had gravitational waves. Gravitational waves has been discovered in 2015, and they were predicted by Einstein. We didn't know at which velocity these waves are traveling. Now we had observed in 2017 a merger of two neutron stars. And since they are not black holes, they can have also a mechanism with matter that is getting out, and like a gamma ray burst, for instance. And in this event, we had 1 second after, we had a gamma ray burst arriving to Earth. So they arrived after a travel of 130 million years. They arrived at 1 arcsecond. So this means that we have a large precision on the gravitational wave speed, which is exactly the light speed at 10 to the minus 15, which is the precision of this. And this is a large progress because now we can constrain the mass of the graviton. The mass of graviton is very small. It's like the photon, which has a zero mass. That's why it goes to the speed of light. The graviton mass has very, very small mass. And you see the constraint here. And also we can constrain theories of modified gravity. Some theories had a velocity of gravitational waves that were different from the speed of light, so they are ruled out. Now we have still some problems. I told you that we have different scale to have the distance. We have a distance with Cepheids for nearby galaxies. We have a distance with supernovae, 1A, and then we have a distance relying on the oscillation of the Big Bang radiation. And here we have a tension now. The Hubble constant, or which is based on the distance, there is a discrepancy with the Hubble constant that we measure in the nearby galaxies. This is 73, and the Hubble constant that we measure at the last scattering surface near the Big Bang. And this means that we cannot make the joint efforts between the redshift 0 nearby universe and the beginning of the Big Bang, which is different Hubble constant, different expansion. So this is one of the mysteries that we are working about here. We're trying to find the tension, and this is very interesting. This is not telling you that you are completely wrong, maybe telling you that you have new physics that you will discover in the nearby future. And now I will finish with some very interesting view I've discovered, and I tried to show you how the Big Bang was accepted by many observations prove the Big Bang. Now we want to know what is exactly behind the Big Bang. And we have some theories that are not yet verified, of course. And this is led by some problems that we have about the horizon. The horizon is schematized there. And already Laura told you that when we are looking far away, we are looking back in time, because of course, if you have a galaxy here that is at 10 billion years from you, the light makes 10 billion years to come here. And of course, if there are galaxies behind the horizon, it will take more than a Hubble time, more than the age of the universe to come to you. So you cannot see these galaxies. So even if the universe is infinite, you will see only inside this horizon, which is the distance, the radius here is a distance that have the light has traveled since the beginning of the universe. But the problem with the horizon is the following. Here you see the last scattering surface that I've shown you. And at this epoch, which is very close to the Big Bang, 300,000 years only, the horizon was very, very small. It was on this map, it was only 1 degree. So on this map, you are seeing 40,000 horizon. And this means that all these 1 degree regions are not causally linked, because you would need more than speed of light to have a signal to go from one region to the next. So they are completely independent. And the problem is why the temperature of this radiation is exactly the same at a precision of 10 to the minus 5. It's completely homogeneous. We've seen that the temperature is 2.73 degrees now, and it was hotter in the past, of course, but it was exactly the same. So why? In fact, to solve the problem of the horizon, we need an inflation that is not only an expansion, but at the very time of the Big Bang, in 10 to minus 32 seconds, you have to inflate your space by a factor 10 to the 30. It's gigantic, enormous. So it will be hard also to believe. It has been taken 1 century to believe the Big Bang. Now, for the inflation, it will be hard. But look at this cartoon. Why it is solving the problem of horizon is because in this very small time, of course, the light has no time to travel. So the horizon is about the same thing, but the space is completely inflated in between. So all what you see here has come from the same part of the universe. That's why it was causally linked. And also this hypothesis of inflation solve the problem of flatness. We have seen that the universe is flat, and it is a surprise because there is a fine tuning. In fact, if it is very small epsilon from the flatness at the beginning, this epsilon is exponentially increasing. So you are not expecting to find a flat universe. But if it is inflating, of course, you see that we are now in the small part of this tangential plane here, which is flat, of course, even if the universe is not flat. And also, the bonus on the inflation theory is that it gives you the origin of the fluctuation that give rise to the structure. Because at the beginning, you have the vacuum, you have the quantum vacuum, which has fluctuation, quantum fluctuation. And if you are able by this inflation to put this microscopic fluctuation to a macroscopic size, because you increase by 10 to the 30 their size, then they will become centimeter-like fluctuation, and then they will be enlarged to galaxies today. So it gives you, in addition, the origin of the fluctuation. But of course, this advantage comes with some problem. This theory of inflation were devised already in 1980s. And soon after, people realized that you can stop inflation in part of the universe, but not in all the universe, not everywhere. So all the false vacuum, the vacuum of quantum mechanics is still going in inflation everywhere except in your universe. So you could form several universes that will not be connected, that could be formed with different physical quantities like the density, dark energy will be different. So you could have different fates for the different universes. But we have this view that was promoted by Andrea Linde, and that we are only a very small, tiny part of this universe here. And we see it is flat here at the border. And we have a lot of multiverses that we will never see, have the opportunity to contact or to see any signal because they are recessing from us with a very high velocity. So you see now that our vision of the universe is much, much larger than people had in the beginning of the 20th century, where we didn't know that galaxies exist. So we have this kind of multiverse. And of course, inflation is not the only theory. We have outsiders like the rebound theory, which is even more difficult to imagine because it comes from the string theory, where you have a 10 or 11 or 26 dimension of space. You have brains. So our universe is a 3 membrane here, 3 dimension. And you can imagine that these brains are colliding and this making a big bang. This was the model of the ekpyrotic universe here. The 2 brains come here, and there is a big bang here and creation of matter here. And then all these brains come back and you have a rebound. So you see, it is not really followed by many astronomers, but there are some people working like that. So I will finish here. The history is not finished at all, but I hope to have shown you how the science is going, how we are obliged to believe in a Big Bang that was hard to believe at the beginning, but now we have complete proof that the Big Bang has existed. It is the adopted theory now. Now we have another theory of inflation to solve the problem of flatness, horizon, and the origin of fluctuation. We don't know if this inflation exists or not. We could find a proof of inflation in the primordial gravitational wave, because if there is inflation, it has produced, of course, a perturbation sorry, in the space. We tried to measure this primordial gravitational wave in the Planck signature. It was a failure, but now we have other satellites that will be launched to prove that. So in the near future, it's possible that we have proven this primordial gravitational wave and that inflation will be mostly favored. So I stop here and maybe we'll have some questions. Thank you.
Thank you very much for that wonderful, very rich, detailed, historic talk. Merci beaucoup. And we have a question from you to the audience first to initiate the question period. And it's now appearing on the screen. How did the idea of the Big Bang become accepted? And so our audience is invited to choose among the options there: overcoming philosophical obstacles, observational evidence, theoretical ideas worked out, or all of the above. I have a note at the bottom that none of the panelists can vote. Take a moment and vote, and we will project the results. And it seems as though the majority did well. Nobody got anything wrong, of course, but well done.
Well done.
Yes. So we had some questions from the audience toward you as well. I'll start with the first question, which has to do with the Big Bang theory. And it's a question about whether, since it's a theory, could it still be considered incorrect? And if so, which alternatives are available?
In fact, no, the Big Bang, in the sense that the universe was very dense and hot, is completely demonstrated now. It's not a theory, it's a fact. we have seen in the radiation of the millimeter radiation in the hollow sky, that there is a completely perfect black body that cannot be anything else than the Big Bang. And also have found by the Hubble Space Telescope, we have been able to look at the primordial galaxies and look at the time where there was many more small galaxies. So there is a big evolution of galaxies, and we are going now to see the reionization epoch, where there was only the first galaxies reionizing the universe, because the universe at the beginning was ionized, and then after some expansion, the universe becomes colder, so it becomes neutral hydrogen atoms. And then when the first galaxies come in, then the UV radiation from stars can reionize the universe. And we see all that. We see the reionization in the quasar radiation. So all the Big Bang is proven now, also by the nucleosynthesis of helium, deuterium, and so on. There are many, many proofs, and nobody is detracting the Big Bang now. So it's really not only a theory, but a fact.
Great, thank you very much. And there was a follow-up on that one about dark matter and dark energy, and whether these could pose challenges for the Big Bang theory.
No, in fact, we don't know what are the dark energy and dark matter, but it's not a challenge for the Big Bang. The Big Bang is there, whatever the nature of this dark sector. Of course, it's possible that the dark sector is only our ignorance about the gravity itself. The gravity can be modified, and people are trying to modify the theory to extend Einstein. You know that Newton was there for a while, and then Einstein came to extend Newton. But when in many circumstances, Newton gravity is sufficient for us. So it's not put in difficulty. It's just that you have to extend it to apply to other circumstances. Here, the Einstein theory will be good for all the solar system. We know it's very well proven, but now in low acceleration, low weak gravity, we have to extend it maybe. So maybe this dark sector would be solved like that. We don't know. It's completely an open question, but it does not challenge the Big Bang.
There was a question about dark matter and black holes. Is there a relationship, if there is a relationship between those two?
In fact, not. It's called black, but it's completely different. The black holes are very compact objects where the gravity is very strong, very, very strong. And in general, what we think, the main theory is that the black holes are due to ordinary matter, the baryons, the hydrogen, protons, neutrons, and so on, that come to form at the end of the lifetime of a star. You have a supernovae, and if the supernovae residual is larger than 3 solar masses, then you can have a stellar black hole. And we have plenty, billions of stellar mass black holes in the Milky Way. And in each galaxy, you have a supermassive black hole. But all these black holes are formed by ordinary matter. They are not done by dark matter, because dark matter is not dissipative. It's not interacting with photons. It's not radiating. So he cannot get rid of its energy. Ordinary matter radiates and it can condense, but the dark matter cannot condense. So when it is virialized, making a halo around the galaxy, it cannot condense in a black hole. So there is no dark matter in a black hole. It's only ordinary matter.
There was a question about if there's any thinking that light might not be the fastest entity.
What, faster? I've not understood the question.
Oh, sorry. Whether light might not be the fastest.
The speed of light is not the largest. In fact, no. We have now the theory of covariance by Einstein is a proof that there is nothing going faster than light. So it's not possible. Really not possible.
There was a question about the perception of space. If everything is expanding, why do we not see any filling? We don't see space filling up.
The space, well, it's difficult to answer this question. Space is filling everywhere. In fact, maybe it's infinite, and you are in this space. So space is filling everywhere. I don't think that space is done by nothing. In fact, it's just the structure of the space that is around you. If there is no matter, it's completely void. Of course, you can have some quantum mechanical virtual photons and so on, but it's a vacuum, in fact. So space, you have space-time, of course. You have a relation between space and time. We have seen that when we are looking far in space, you are looking back in time also because of this finite velocity of light. But it's difficult to, to answer this question because it's a perception that every people has to have.
I had a question about the image that you showed by Lindy in 2007. The image itself resembles something from my area of evolutionary biology. And I found it very interesting that at one point of the diagram, there was a crossing of the trajectories, if I could call them that. Is there any significance to where they cut across each other like that?
No. In fact, they are linked, but they are not touching each other, in fact. So it's just a way to plot. In fact, we don't know. There are several universes, and in between there is a vacuum.
Mm-hmm.
So there is no link.
No link at all.
It was a way to make the cartoon.
So I think in your talk, you very nicely showed how ideas from the past can resurface in the future. In particular, I was thinking of the quantic vacuum.
Yeah.
And I wondered if scientists over the last century, perhaps, have learned to recognize when a field is mature, or if it's still an unknown. We never know when something might come back from the past to become useful again.
Yes, it's a very good question, and I think it's for historians of science. It's very interesting because, for instance, the lambda of Einstein that he put like a garbage, and then 100 years after he came back because we had proof that lambda is there. So this is quite interesting, and people cannot predict that. In fact, we know that part of our theory is mature. We have seen that the galaxies, for instance, we know a lot more about galaxies. We observe them. We are just looking at details, how they form stars, how they quench their star formation, and so on. But we have nothing fundamental about that. I think it's a theory which is rather mature. There are still many things to learn, but we are not going to learn except the dark matter, learn more about that. What is not mature is the nature of dark matter and dark energy. This is completely the beginning of it, maybe a new theory. This we can recognize that it is a starting point. We are not controlling anything. For galaxies, except for dark matter, we are thinking that we are controlling more or less. But this is the quantum mechanics, yes, at the beginning, there was a lot of revolution in the beginning of the 20th century. And now we think that there is a second revolution about the way to control atoms and photons one by one, and maybe making some quantum computers like qubit and so on. This is the beginning of a new revolution. We are feeling that. We don't know what will happen, but we are feeling that we are witnessing a second quantum revolution. And there are some progress like this. And sometimes people say, well, in this sector, we know everything. And it's not true. We have to be humble because it's never the end of it. And we discover always something that is more and more.
Yes, we know just at the dawn of quantum mechanics, that same sentiment was permeating the field, that once we understand quantum, black body radiation, everything is known. And you also very, very nicely showed the role that humans themselves, their intuition, their biases play. And just thinking about Einstein, both in terms of the way relativity was received initially as from a very skeptical audience, but also Einstein's own biases in formulas and constants and so on. And I wondered if you thought that the role that individual biases and shifts in ways of thinking play in science.
Oh, yes, it's very interesting to point this out because indeed the individuals have their biases. And for instance, Einstein had a great prestige, of course. He discovered the general relativity with his mind. In fact, there was no proof of that, and the proof came afterwards. So it was a genius, kind of genius. And that's why he has a lot of prestige, and people followed him during 1 century. If there was no Einstein, in fact, people would have discovered lambda much before, I think. So there was some delay because of this prestige of Einstein. Also, Einstein did not like quantum mechanics. He said, God, don't play dice, for instance, and all this uncertainty principle he did not like. He also predicted from the gravity the black holes, and he did not believe that there were black holes. In fact, you can imagine he was these black holes, that the existence of black holes, that some objects could have escape velocity that is larger than velocity of light, so even light cannot escape. That was predicted even in the 18th century by Laplace, Pitcher, and then of course it was an idea. And then Einstein said, yes, we could have black holes, they are in the equation, but it is an absurd idea. They will not be, it's not realistic. They're only an equation. It's only Penrose in 1965. All astronomers were not convinced that black hole existed until 1965. And why? Because they said, well, of course, if you collapse a star after the supernovae, it could come a black hole. But the collapse were done relativistically, spherically, because it's not possible to solve the equation if it is not isotropic. And people said, well, it's unrealistic. What happened is that there will be an angular momentum, rotation, and all the matter will fall apart because of the rotation, and there will be no black hole. So what Penrose did is that he make this topological demonstration that it was inevitable in general relativity that after the explosion of a star, you will have a black hole. It was inevitable. And that's why he had in this year the Nobel Prize with in 2020 with all the discovery of the black hole in our own Milky Way, because it was the first that to demonstrate that the black hole should exist inevitably, and all astronomers followed. So you see, one demonstration by an individual can change all the opinion of the majority of astronomers.
Thank you very much for that answer. It's having mentioned Brian Schmidt and Penrose, the Origins Institute has hosted both those speakers, and now hosting you makes a complete trilogy. So thank you very much for those answers and for your talk as well. It's now time to open the discussion to the panel. So the other two speakers from earlier this morning, Dr. Janvier and Dr. Parker. And we do have some leftover questions, but maybe we could start the discussion with some concepts that kind of permeated some of the talks. The relationship between observation and theory and the role that it plays in science, I think is one theme that has permeated all three research programs of our speakers this morning. So perhaps that would serve as a starting point for a brief discussion.
Well, I think that's definitely a connection between all different areas of science, but particularly my experience in galaxies and cosmology. It's been a competition over the last century at times for whether the theory is leading or the observations are leading on various issues, and some of which we heard about during the last talk. So ideas like lambda may have existed in theory at earlier times, but it's the observational evidence many decades later that then starts to lead the field anew. And so I find it interesting that over the history of science, we can have at times where a new discovery in the lab or with the telescope can lead to entirely new theoretical ideas, or we can have ideas that fell out of the theory and it takes decades to have the technology to actually test them. So some of these current ideas in cosmology, like inflation, The early inflation papers are now 40 years old, but it still remains incredibly difficult to test observationally. So that's an example of theory leading observations.
I can jump in. I think it's yeah, I guess it's really interesting, and sometimes we think that because space physics is a closer to Earth than other galaxies at least, and black holes, that it's the observation leading, but actually there are a lot of things that we don't know. And well, what I want to say is that whenever we have how to say that, measurements in space, they are so local that we don't actually get the full picture. And one example, for example, of the theory leading is the solar wind. The solar wind was something that was, there were a few theories, and we saw that there was something that was static and not actually something flowing out from the sun. And we needed to have the observations with the space era, and to get the observations that really validated the one theory that nobody really believed in at the time. And it was a theory that was proposed by Eugene Parker. And Eugene Parker is actually the only person alive that has given his name to a space mission. So for anyone who is interested in theory, that's something that can happen in your lifetime. But keep that in mind.
There is a leftover question for Dr. Janvier, which we can use to bridge to another topic, and that would be about predicting space weather. And Professor Combes nicely ended her talk with talking about computers and the role that they play nowadays. And I wondered if artificial intelligence might play a role in any of your fields, because we're in the era of big data. And so artificial intelligence can lend its hand, as it were, but you can answer the question first about prediction of weather in space.
So I would say there are two levels. The first level is trying to understand things from a scientific point of view. And this is rather, I would say, complicated in terms of really predicting. So we know that the sun has a solar cycle. It's around 11 years. So we know, for example, now that because we are entering in a solar cycle, the sun's activity is going to get bigger and bigger. We also know that most of the space weather events come from those regions of the sun that we call sunspots. So we also know that when we have a sunspot, the likelihood of having some space weather activity is higher than when the sun is completely quiet. But to predict from an operational point of view, to say tomorrow at this time we're going to have this particle storm of this intensity, we are nowhere that yet. And there comes the second level, which is more the operational side, which is more about statistics and trying to get what are the chances of having something. And I would say that we're still at the beginning, but we have, someone asked, what's the time delay? When we have a particle storm, the time delay is very, very short, because particles travel almost at speed of light. So it's around 8 to 10 minutes. But when we have those solar storms, we have a few hours. And because we're monitoring the sun all the time, we can now have, I would say, operational tools that give us an idea of what's the direction of the storms. Is it going to hit the Earth front on or at the flank? Because of the speeds that we can calculate at the sun, we can kind of guess when it's going to arrive at Earth. So for that, we do have operational, predictions, but not to the point that, again, we know like what's the intensity, when exactly it's going to come to arrive at Earth. And you asked a question about artificial intelligence, and that's a really hot topic at the moment in the field. And I guess that, again, I would say that that's something that we're trying to apply, because we've got a lot of data, and we are actually working with some students at the moment on trying to feed a deep neural network with images of the sun and try to understand what's the reaction of the geomagnetic activity, so the activity of the Earth's magnetism. But that said, that doesn't give us the scientific understanding. So we also need to at the same time come up with some analytical solutions, theory, and a full understanding of what's going on in the black box that is the deep neural network. But that's definitely something that we are working on at the moment. Yeah.
I have a question, if I can ask.
Yeah.
In fact, is there some analogy between normal weather that we have it on Earth and space weather? Because in normal weather, we have some chaos. It's chaotic. So in fact, instead of taking equations, the Vlasov equation or so on, we are taking the weather of previous days, and we are trying to make an empirical situation to predict the future. So is it possible that in the sun it's also chaotic because you have magnetic field, but you have particles in the where, and at some point you will be obliged to take some situation and then predict the future like that?
Yes, so there are already some, it's a really interesting question. We have those models that are, it's not necessarily chaotic, but it's how to predict events that are going to happen, for example, whenever you have an avalanche or a sand dune that collapses, or a volcano that is going to erupt, or even the stock market that just collapses. And we try to apply this kind of models that are about what happens before, and suddenly there is a huge event that is happening, and we try to apply that for flares, so those brightenings that are happening at the sun. But the problem is when you talk about chaos, or when you talk about those kind of events, they're really, really small events that are accumulating and leading to something huge. The problem with storms and solar storms is that it's not really chaotic in nature. It's structured, it's huge. So it's not like those little events that are happening in the sun's atmosphere. Is this huge magnetic field that is going to be really structured for days and days, on which you cannot apply chaotic physics or a chaotic chaos approach. So we have those two levels, and we're trying to match them, but we can't at the moment.
Maybe I could just add to on the galaxy scale, that question of artificial intelligence. The astronomers have always been the holders of big data sets. So we've also been pretty early adopters of techniques to deal with big data. And some of those techniques come from artificial intelligence, machine learning. So in my talk, I was talking about the shapes of galaxies, and that's been an application where it's been really popular to apply machine learning algorithms, where you have some training set where experts who are used to looking at galaxies have identified the shapes, various properties of the galaxies. That's your training set. And then you apply that to some massive survey where maybe you have millions of galaxies, where you don't have the time to look at millions of thumbnails and classify the galaxies. And so you train a neural network to do that work for you. And so there are definitely lots of examples of applying machine learning to sets of galaxy data.
Thank you for that. In your talk, you drew many analogies, or maybe you don't see them as analogies, to evolutionary biology. Maybe it's more natural for you to see it in an astrophysical sense. But I was really struck by that. And one area that is problematic in evolutionary biology is when hybridization occurs. And when you were talking about mergings, it made me think, oh, so that's where the analogy might start to break down. But then it occurred to me that a really ripe area of research right now is a process known as horizontal gene transfer, where material gets transferred between individuals from different species laterally rather than vertically, generation to generation within species. And that has provided a rich playground of research. And I wondered if in any of the processes you discussed, there's any exchange of material between galaxies, maybe not when they merge, but if they kind of come close enough?
Well, so the interactions of galaxies can be dramatic, where you have a merger. Take two galaxies or more than that, and they merge and they become one object, and then everything gets completely mixed. The other thing that I didn't have time to talk about today, which happens very often, including right now in our own galaxy, are when little galaxies, which we call dwarf galaxies, infall onto a larger galaxy like the Milky Way. Milky Way is pretty big. Our nearby neighbor Andromeda is pretty big. And part of the way we've grown is by shredding, or sometimes called cannibalizing, small little galaxies that fall into our gravitational potential well. So actually around the Milky Way, there are streams of stars which all have the same, they're all moving together. And that's because they all came from the same little galaxy that's been shredded by the gravity of the Milky Way. So I have no idea how that connects in an analogous way to biology, but it is true that large galaxies are built up by shredding, in part by shredding small galaxies, which are over time just subsumed into the big galaxy.
Right.
You can have also flybys, that is only exchange of mass without merging.
Yeah.
Flybys, was that flybys?
Flybys
is two galaxies are in a hyperbolic orbit and they exchange mass, but then they go away. They don't merge.
Okay, yes, so that would be similar. I was wondering if any of you would care to comment on the role that serendipity plays in your field, or has played historically in your fields. Are there any famous examples of serendipity? I know that Professor Combes mentioned the background cosmic radiation with the distorting noise in the antenna. Are there any other famous examples of serendipity in your respective areas?
Yeah, this is actually one of the reasons why, so most of my research is statistical in nature. So I don't study a nearby galaxy in lots of detail. I study hundreds of thousands of faraway galaxies and try to understand on average what happens. So I don't necessarily need to look at images from telescopes. I can do everything algorithmically. Here's my image, automatically find the galaxies, automatically measure their sizes, colors, and all that. But sometimes it's really worthwhile to look at images because you will see strange things. Those could be artifacts in the observations, or sometimes objects you might not expect. And one place where this has happened in an interesting way is through a citizen science project called Galaxy Zoo. So one of the ways to deal with huge sets of data where you don't have enough time for professional astronomers to look at all the images is to do machine learning. Another approach is to employ interested citizens. And so there's been this very successful project called Galaxy Zoo, which you can register for. And citizens look at images and classify the images. And there have been a couple of unique kinds of objects identified through these massive citizen science projects that we didn't know about. So one example is something called green pea galaxies. Very small, very, very compact, green colored galaxies. Green because they contain a lot of an element of oxygen that emits at green wavelengths. So you see this green glowing little ball. And because they're rare, you don't find them if you just look at a few random galaxies. And you may not find them with an algorithm because you haven't designed the algorithm to find them. But by having people look at millions of images, you can find serendipitous things that you didn't know existed. So that's one example.
There are good examples also in the discovery of objects like pulsars. In fact, there's a very good example of Jocelyn Bell that you know. She was doing a PhD thesis looking at quasars, because the quasars in the 63 were just discovered by Martin Schmidt. So they built a telescope to look at quasars, and finally she found little bumps that they were little green men sending signals. And finally it was pulsars, so completely serendipitous. It was neutron stars that were pulsing. There was a serendipitous discovery of a new object.
And it would be a shame to let that discovery be noted without noting on this panel of women astronomers and space scientists that discovery led to a Nobel Prize for Jocelyn Bell's supervisor and not for her. And she's the one who made the discovery. So one of the great oversights of many of the Nobel Committee over the years.
Thank you for that.
If I can tell, I guess one big thing that happened in the field of solar and space physics, and at least for the connection between the sun and the earth, is this event that we call the Carrington event. And I think someone has asked about the possibility to have a big Carrington event, which is basically a huge solar flare that led to auroras. So auroral activity is linked to geomagnetic activity on Earth. And I think auroras could be seen all the way to Mexico. So there are some newspapers that said that you could even read a book at the light of auroras, which for me is kind of really, really interesting. And it's one of the major events that we know. But we also, I guess, in terms of serendipity, the thing that I'm thinking about is it was seen, so the flare was seen at the sun by two British astronomers, Carrington and Hodgson. And I kept thinking, what if they didn't see it? I'm sure we would have seen it, maybe later, but it's one of the major in recent history flares that really had big consequences on Earth, and we could really see them at the sun. And apparently the story is Carrington didn't believe that he could see something really so sharp and visible on the surface of the sun. And when he called his assistant to come and check, the flare, the flash had already disappeared. So, what are the odds really of saying that?
There will be a number of schools tuning in, and I wondered if you would share maybe a personal anecdote or a motivating factor, a book, maybe a movie that motivated or inspired you for the career that you've chosen.
Just one? Or?
Well, as many as you like.
So I like I like to tell a story that I think for me there were three things: E.T., the movie E.T., the X-Files, and Contact, and all have to do with aliens. And when I was little, I just wanted to discover aliens. I wasn't good at biology, but I wanted to do exobiology. So that because I wasn't good at biology, I went into astrophysics. I mean, physics and astrophysics instead. But yeah, for me, alien life was just a major a major incentive to go into the field.
So for me, I was not the kid who always looked up at the night sky and always wanted to be an astronomer, but I was a kid who always asked why. So if you speak to people who knew me when I was young, I was annoying because I just constantly asked the question, why? Why is this? Why is that? And so as I went through my education, I continued that interest, which meant I took as many sciences as I could. And like many people, part of the reason for the trajectory I'm on is because I had a phenomenal teacher. So at the beginning of university, I had an astronomy professor who was phenomenal. I ended up doing research in his group. That was my first research experience. And if I had had an amazing person teaching me neuroscience, maybe I would be in neuroscience now, but I got really excited. And I think that's a good message for kids too, that if you're interested in science, just keep doing it. And no matter which direction you go, there's really interesting questions to work on. So you may start being interested in astronomy and you might pivot to something else. And there's lots of exciting questions to work on in all these different areas.
Yes, for me it was the same as Laura. I was not an astronomer when I was young. I was not attracted by the sky in particular, but I was attracted by science in general. And maybe biology was attractive also for me. I was attracted by new discoveries, in fact, that was made an impact on our understanding of the universe. Either Copernic with his evolution, but also Pasteur with making vaccination or whatever, which was a progress in humanity. So this was attracting. Of course, I look at the Apollo television. Of course, it was an excessively interesting movie. But I was not attracted by the sky at the beginning, and it came afterwards by the theory, cosmology.
And were there any surprises for any of you once you were in the field, steeped deeply in the research, that you didn't foresee before you got into the field?
When you are in the field, well, it's so attractive that you keep in. You discover things, you discover small things, you hope to discover bigger ones, and you never stop. This is my experience.
Yeah, I think that was a big learning curve as you become a professional scientist, that the so-called eureka moments that you learn about as a kid are really rare in the history of science, that science is made by us all incrementally attacking interesting problems at the moment. And so that's definitely something something that I only learned, I think, a little bit later, that it's unlikely one paper you write is going to change the entire field. Instead, there's a body of work that builds up over time, and we keep making these small but important steps forward in our understanding.
I think for me, it was that, so I actually didn't end up studying astrophysics. I went into fundamental physics and I specialized in fusion science, so basically trying to reproduce a star on Earth. And I thought that because everything is plasma in the universe, I could, study galaxies, I could study stars or whatever. So after my PhD, when I turned to, professional research, I thought that, they were all talking to each other. And I discovered that actually, as you get specialized, you just get, more and more narrow in the field of what you know. And I think that was the, how to say that, it's at the same time, it's really fascinating because there are more and more questions. And at the same time, there's a bit of this deception that I will not get to really understand other fields of astrophysics that really attract me. So that's the problem, I guess.
Thank you for sharing that. I think occasions like these where we can bring together people from different backgrounds, although from the outsider's view, they might be very similar. They are very different. And I think to share ideas and anecdotes and histories, I think it's very important. And we thank you all for your time and your contributions today. And we invite you and the attendees at home around the world to tune in again tomorrow for the second half of the symposium. But thank you all three very much for your contributions here today.
Thank you.
Thank you so
Thanks.
much.
Bye-bye.
Bye-bye.
Au revoir.